Hello everyone, welcome to my Chem Corner. So in today's class we are going to do some more Intext questions from chapter 1 solid state of class 12. So the next question for the video is 1.16. Which of the following lattices has the highest packing efficiency, simple Q, BCC or FCC? So as we have learned in the entire chapter, we have learned a complete derivation of packing efficiency for simple Q, BCC and FCC or HCP. So these are the basic structures of these unit cells. Now from this we learned packing efficiency from the derivation for simple cube to be 52.4%, BCC 68% and FCC 74%, which is for HCP. So we generally say that more the percentage of packing efficiency, more is going to be the percentage, more is going to be the packing efficiency of that particular unit cell. So in this case, HCP has the highest packing efficiency as the percentage of that unit cell is the highest. So here the answer is HCP. Now the next question is 1.17. Now here the question says an element with molar mass 2.7 × 10⁻². kg per mole forms a cubic unit cell with edge length 405 picometer. If its density is 2.7 × 10⁻³ kg per meter cube, what is the nature of the cubic unit cell? So from this question, what are the values given to us? We are given with M, which is the molar mass, which is 2.7 × 10⁻² kg per mole. We are given with A value, which is the edge length, that is 405 picometer, but we need to convert this to meters. So it will be 405 10⁻⁻12 meters. The next one is density, which is 2.7 10⁻³ kg per meter cube. We are asked to calculate the nature of the unit cell, which means Z value. So from the density formula, we know density, we know molar mass, we know what is A. We can then cube it. Na is going to be a standard value or a constant value. So from this entire equation, we need to calculate what is the value of Z. So once we substitute the values in with these equation, for D we have 2.7 10⁻³. Then we have the value of A, which needs to be cubed. Then we have the value of Na, which is a constant 6.022 10⁻23. And the last one we have is the molar mass, which is 2.7 10⁻². So when we calculate all of this, that Z is coming to 4. So here when Z is equal to 4, the nature of that particular unit cell is an FCC, because when we calculated the number of atoms per unit cell for FCC, Z value was 4. So in this case, with these values, the nature of the unit cell is a face-centered cubic unit cell. Now the next question is question number 1.18. What type of a defect can arise when a solid is heated? What physical property is affected by it and in what way? So totally 3 questions. First, we'll try to understand what do you mean by when a solid is heated? What happens? So if you see here, there is positive, negative ion, which are denoted in these orange and gray dots, which these are arranged perfectly. Therefore, this is a perfect crystal. But in the next one, it is showing that when we heat it, one positive ion and one negative ion is not there. It is missing from an entire lattice. So here, when a solid is being heated, the constituent particle can leave the lattice side and it can create a vacancy. So here, if you see, positive, negative ions are missing and a vacancy is created, which is a vacancy defect. So that answers the first question. Now the next one says which physical property is affected by it. Now whenever this happens, we look at 2 physical properties. One is the volume, the other one is mass. Now in this case, the volume is going to remain the same. There is no change in it. But what happens to mass? The mass is going to reduce because these have moved out. So the mass is going to decrease. When mass decreases, the density of that particular lattice is also going to decrease. So 3 questions are answered here. First one is what happens when you heat it. Second is which sort of a physical property is affected. We know density. In what way is it affected? The density is going to reduce. Now the next question is question number 1.19. What type of a stoichiometric defect is shown by ZNS and AGBR? So before we jump into trying to analyze what it is, let's see what are the stoichiometric defects that we have and what does stoichiometric defect itself mean. So stoichiometric defect meaning the stoichiometry or the ratio of particles are not disturbed. No matter what you do, the ratio is not being disturbed. They are also called as intrinsic or thermodynamic defect. Now, under stoichiometric defect in our syllabus, we have learned two types. One is Schottky defect, the other one is a Frankel defect. Now, Schottky defect meaning these are observed in cation and anion of comparable sizes, which means the cation and anion can be of almost similar size. But Frankel defect is observed where they have a huge difference in the size. Now, based on the size, we can tell whether ZNS is going to show Schottky or Frankel, or whether AGBR is going to show Schottky or Frankel. So here we can say that because the difference between the silver and bromine atom is not very big, thus they are of almost comparable sizes, they can show Schottky defect. And the other one, of course, Zn is a much bigger one and sulfide is a smaller one. Therefore, they have a huge difference in their cation anion size. Therefore, this will show Frankel defect. So zinc will have a smaller size, sulfide is much larger. Therefore, zinc sulfide will show Frankel defect. Schottky defect is shown by AGBR. Now, we have also learned one of the classic examples that AGBR can also show Frankel defect. So both can be shown by AGBR because they have a little bit of difference in size, but they are also comparable sizes. So that answers your question number 1.19. Now, next one is question number 1.20. Explain how vacancies are introduced in an ionic solid when a cation of higher valency is added as an impurity in it. Now, I've done a detailed video about this. It's nothing but impurity defect. So here I have a lattice of NaCl, but at one point I have another atom of a higher valency sitting there. So what is happening? So here what we're going to do is consider crystallization of molten NaCl with small quantities of strontium chloride. Now remember, Na is with a +1 charge, strontium is with a +2 charge. So during the process, what will happen? Some of the Na atoms are going to be replaced with a strontium atom. So to replace one strontium atom with sodium atoms, you need to remove two sodium atoms because the valency of sodium is, the oxidation number of sodium is Na +1, whereas strontium is +2. So two sodium atoms need to come out to sit to accommodate one strontium atom. In order to maintain neutrality, that entire process needs to happen, where two sodium atoms are lost to accommodate one strontium ion. Now, when this happens, what happens at one point, there is a vacancy created, which is a cationic vacancy. Therefore, the number of cationic vacancy produced will be equal to the number of strontium ions that are introduced into the lattice. So if there's one strontium ion, that means one vacancy will be created. So this is going to answer your question number 1.20. Now your next one is 1.21, which says ionic solids which have anionic vacancy due to metal excess defect develop color. Explain with the help of a suitable example. Now this also had explained in detail in the video where I spoke about your defects in one of the videos. Now here it says sodium chloride crystals, when they heat it, what happens is sodium atom is going to come out. Now when sodium atom comes out, what will happen here? An electron will sit in place of that sodium atom. Now what is happening to this particular electron when it is heated? This electron is going to absorb light of a suitable frequency and it is going to give color to the flame. Now that color is the reason why you get barium. For barium you get apple green, for strontium you get crimson red. The reason you get a flame is because of this one electron. When it is heated, it gets excited. Now this particular center where an electron is there and that's responsible for a color, that center is called an F center, or it's called as Farben center. Alright, so this is going to be the detailed explanation of question number 1.21. Now the next question is 1.22, which is the last question in the chapter. A group of 14 elements is to be converted into N-type semiconductor by doping it with a suitable impurity. To which group should this impurity belong? This also I done an entire detailed explanation for this when you're trying to dope it with another group to form an n-type, which means you need to have negative electrons. So here you need to have more number of electrons in order to get n-type, because n-type meaning negative type of an semiconductor. So in this case, you need to dope it with a group 15 element in order to get an n-type semiconductor. So I hope this video is helpful to all of you, because I have tried to answer all possible questions that are there in this entire chapter, and I hope it's clear. If you have any further suggestions, please don't hesitate to put it in the comment box. I have seen a lot more of suggestions that are coming up in the comment box, and I will be doing a video of all of that very soon. So I'll see you in my next video. Until then, stay tuned.